we are interested in not just subjecting the soil to high gravity and create prototype stresses, but we also want to study earthquakes. Now, centrifuges can apply, it's like applying load in the vertical direction. But earthquakes don't do that. Earthquakes apply loading in the horizontal direction, right? That's what we are interested in. You want to shape the model while it is spinning around. So you need really, and this is the tricky bit, powerful earthquake actuators to apply large forces fairly quickly. And again, this is a consequence of scaling laws. I'll come to that in a second. But you need to apply of the order of 10. Okay? So you need this actuator to fly on the centrifuge. And at lunchtime, we were talking about shaking tables. Effectively, what we need is a shaking table which flies on the centrifuge and shakes it. And structures people think that they have done very well by constructing a shaking table, which will work at 1 G. We need to do that at 50 or 100 G. So it is a much harder problem for geotechnical engineering. It is always going to be more interesting and difficult than our structural colleagues. And they make all the money. So there are several versions. I will come back to this and go a little bit more detail later on. But the earliest version I built was called the stored angular momentum earthquake actuator, or in short, SAM actuator. It turns out Schofield's grandson was also called SAM, so the acronym kind of worked. And the idea was to build it in-house cheaply. And all of that costed me under 19,000 pounds. I mean, that much money you can find in the back pocket of your professors, most professors, like Professor. So it's very cheap to build. You can, but there's a trick to this. The most critical part in all it is you're storing a lot of energy into flywheels, like you would in a car. But then you need to transfer all that energy quickly into the model. And for that, you need a fast-acting clutch. And I developed a fast-acting clutch. It took me 6 months of my life. And no amount of geotechnical engineering would help me there. It's a complete mechanical problem. And we built that and tested that a fast-acting clutch could be made and delivers this forces quickly. But once we've done that, we had an earthquake actuator, which can go up to 100 G. We can fire earthquakes up to 100 G level. We can choose whatever frequency we wanted between 1 to 5 Hertz, which is typical earthquake frequencies, magnitudes of up to 0.4 G, and you can make the earthquakes short or long as you wanted, because that only means how long do I hold on the clutch for. And it produces fairly beautiful sine waves like this. So you could get sinusoidal motions, and the fast Fourier transforms tells you exactly where the energy is focused. So this is NIT. And that produced about 10 or 12 PhDs for me. So it was worth my 6 months. Then we got ambitious and started to think about making a servo-hydraulic actuator. But again, in true Cambridge style, we wanted to build this ourselves. So we bought the mechanical valve from a company, but the rest of it we designed and built in-house. And one advantage of doing that rather than buying the whole unit from somebody is that if something goes wrong with this, I'm quite confident to take my screwdriver, open it up to its component beds, and fix it again, because we know every component. Buy, for example, you may have bought a cyclic triaxial kit. How many of you are confident to open the driver and change the controls on that? Very few. You look at the manual. If it does what the manual says, you do your experiments. Otherwise, you pick up the call service, right? We don't like doing that. If it is cyclic triaxial, it's probably okay to do that because it's more common. But there are only 2 or 3 companies in the world which can build things like this, and they're always on the other side of the world. And they'll take 6 months to come in the 6 months motivation issues have nothing to do, and that's not acceptable. So we build this ourselves. So we built a servo actuator like this. This one can go up to 80 G from the earthquakes. Interestingly, we designed this to have a peak ground acceleration of about 0.5 G. 3 weeks back, we had to do some unusual test for a structures colleague of mine who wanted to break some shells under the G. For don't ask me why. And those damn shells were only breaking if we applied 1.3 G prototype acceleration. So we're going at 60 G, and 1.3 times 60 is about 80. Found way better than what the design here suggests. So we are a lot more confident with it now. But the big advantage is that now we can apply not sinusoidal motions only, but any realistic motion you want. I'll come and show some of these things later on. But once you build this, you load it. First time you fire this thing is always fun. And this is the picture taken when we were testing it first time. You can see my hair was a lot darker and I was looking much younger. Maybe same size as now, but certainly a lot healthier. It takes a lot out of you when you do this. It's fun, but it is also pressure. Because a lot of things can go wrong. Things are flying at 200 miles an hour, and each of those blue cylinders I've shown you has oil in it at about 280 bar pressure. So you need a lot of energy to shake the motor. So you need to pressurize the oil to really high levels. So this is fun. But then it does something like that, where the top slide shows you the Kobe earthquake motion, which we programmed in. The bottom one is an Imperial Valley, much longer earthquake, and it's great, but it works. It's fun.
How does it compare with the actual
This is what we actually measured afterwards, but you can compare with what we programmed in, and the frequency it matches perfectly. That's what those valves are made for. But the amplitude, you have a transfer function, so you adjust the transfer function to what you want, so that you get what you want. But in centrifuge testing, normally you apply the motion approximately, but measure it very accurately. So you know what input motion is going from the bedrock into the ground accurately. You normally use more than 2 or 3 instruments to measure just that. I'll come to applications, but as I said, post-lunch, to keep you interested, I'm going to talk about a fun one first. This is something we've done for a BBC program. So this is part of your exercise in the evening. Today you're going to watch a YouTube video. Okay? The program is called The Lost Cities of Sodom and Gomorrah. It's part of their ancient apocalypses, and I checked it's available on YouTube. Okay? And there was this theory that these 2 cities in the Old Testament disappeared into the ground because the people of these cities were bad. So we'll ignore the religious part of it. But there was a geologist who said, if there was liquefaction and lateral spreading, is it possible to lose cities like this to ground? Another example could be our Dwaraka, which is also claimed to be gone. There is another current program for draining the oceans, if you watch Discovery Channel, and they were talking about Alexandria as city of Egypt, which is also disappearing. So is this a legitimate mechanism for explaining historical disappearances of cities? We've done these tests, and I got some hate mail from Seventh-day Adventurists and all kinds of religious groups saying some things are not meant for science to study according to. Anyhow, we'll take that with a pinch of salt. But we had an archaeologist on board and there was a geologist on board as well. My job was to just see whether we can uh, mimic the simulation of the earthquake part and see lateral spreading happens. So in a simple way, you can show this. Before the earthquake, you have a village, town, whatever, on a slope, and that's the sea level. And after the earthquake, you got lateral spreading causing the whole town to disappear. We had to show this with some instruments, and to give credit to BBC, they just didn't want a mock-up test. They wanted us to do a proper scientific test, and as a proper scientific test costs you proper pounds, and they were willing to pay the pounds. So we said we'll do the proper test then, and we did. And that's what they did. They were with us for a week and filmed us every day. It's a horrible version of me. I don't think you can hear it, but basically you can watch this on YouTube tonight, as I said. But what they paid money is for this. You have these measurements coming from the instruments. We wanted to show what the input acceleration was, what the surface acceleration was, and what's in the buildings. What do you see there? So I'm putting an earthquake which is about 0.1 G, 10% of the G level. And you can see at the surface, the accelerations are quite small. And this is quite common in liquefied ground because, okay? It's okay, you're good. Don't worry. I thought HDMI did that automatically. Never mind. You can, once the ground liquefies, it cannot transmit the acceleration. So what you put at the base will not get to the surface. And of course, the instruments are showing that. Building seems to couple better, and they are picking slightly bigger acceleration compared to ground itself. So that's the first proof that it liquefied. The second proof, of course, is we can put instruments in, low pressure transducers, and measure the water pressure. So you can see at the base, it picked up to 150 kilopascals. You know your vertical stress, you can work out whether it's liquefied or not fully, and also how long it takes to dissipate. And you can look at the more surface level flow pressures and show how long they are holding for. Because the surface level water pressure holds on for so long, that means that it's getting fluid from below coming to the top, and that keeps the soil liquefied for longer. In this case of lateral spreading, that's important because that is, as long as the soil stays liquefied, it flows horizontally. So the amount of lateral spreading you get is a direct function of that time you hold the flow pressure for. So mechanically, it should make sense. Then you can look at what happened to the model afterwards. For example, when I look at this, you can see those sand points coming up. So again, that is confirmation that it all liquefied. So they were very pleased. Visually, they had something. They had some data to claim it to be a proper scientific experiment, and they thought all the taxpayers' money was well spent on us. These are our rudimentary models we made, but we made them to have the same pressure as what they wanted. They have wanted some tall buildings, which is representative of that 5,000 years ago, and some short buildings, huts and things like that. And we showed how much they moved horizontally. But this is where BBC's creative geniuses get into action. And and then using our data, they animated this. So this is the earthquake happening. People running. There was some sulfur deposits which got higher, and they got that lateral spreading, moving the buildings along. Now, this program was made 15, maybe a bit longer, 18 years ago. Wasn't that looking like the satellite pictures I showed you earlier, which happened last year? Now, two things. One is to rejoice that it seems that we understand lateral spreading happens and how much it spreads and so on. The bad news is that in the last 15 years or in the last 50 years, we are not able to do a thing to stop this from happening. So, if you're an optimist, you'll say, yes, we are capturing the right mechanism. If you're a pessimist, you'll say, what the heck, we can't do anything about it. But I leave that judgment to you. So these are like fun things we did with the centrifuge, and we can, as I said, do Google ancient apocalypses. It's still there on YouTube. There are other things which I want to talk about later, so about pilots, which I don't want to spoil the surprise now, because I want to go through this detail. But increasingly, we're getting into a situation where coastal protection is getting important. I'm talking this particularly because of the Indonesian tsunami and this part of the world got really affected. And I haven't traveled to Nagapattinam yet, but I'll be surprised if I find a great sea defense wall there, because we don't work like that. We wait until things happen and then worry a lot when they happen and cry a lot. That's not how engineers are supposed to be. We need to fix things ahead of time. So this is one example Ross Bullinger, my friend, has given me. You can see the size of these things. A car there or a human being standing next to it. This is when people talk about coastal defenses, this must be the size of them. This is in California somewhere, and I'll show you examples of what they're doing in Japan in a second. So it's going to cost money, but that's what it takes to protect populations. Now, as a society, we either pay for it or don't. But that's not my call. That's a politician's call. But solutions exist, and at least we can prove how well they work or they don't work, and how do they work. So you can. This is the general idea that you can have a gravity zone, create a reclaimed soil, and put it in front of the sea. Another one is looked at recently in Cambridge by my colleagues. This is an idea of the Japanese, and they're very good at drawing cartoons like this, where you got the city to be protected, incidentally called Kochi, not in your Kochi, but the Japan Kochi. It's spelled exactly the same. I nearly booked my flight to the wrong Kochi once. And Kochi is in the tsunami suspected area. It's a coastal town, and they want to do something about it. And what they want to do is to make a double wall like this, what they call jewel row retaining wall. And there's something special about this, which incidentally the Japanese did not realize. So they want to drive two sheet pile walls and join them at the top. And it's done by a company called GIAN who work with us. And the idea is that, of course, 2 or 3 meter high sea defenses did not work. We all seen these images before. They send iron plate, and you get ships ending up on top of buildings and all the bad things that can happen. I'm not going to dwell too much on that. But this is their idea. Is you drive the sheet pile walls, fill the gap in between the soil, and have tie roads on the top. When they came to us with this idea, we said, what do you think the soil in between the sheet pile wall does? They just wanted to fill it so that they can sell to their clients, that people can have a leisurely walk or running, morning jogging thing along the coast. And for that, obviously, if you have 2 walls with nothing in between, and nobody wants to buy them. If you fill it up with sand, then you can make a pavement, you can have a road or a leisure path like that. turns out that the stuff you put in between the walls, which they didn't design for or had thought about, makes all the difference in how well these things work. So they, like always, Japanese think of something, they don't hang about, they already constructed half of this. You can see the sheep wall being driven in along the coast. So the problem you're looking at is something like this, where you got the two retaining walls, the soil in between, and using numerical analysis, you can see what's going on. I'm not going to explain the centrifuge test and the numerical analysis. These are being published by the authors, but I borrowed a few of the slides. And this is the only slide I want to show you. And this is all the thing you want to know. Red is obviously bad, it's fully liquefied. And you can see when the soil is fully liquefied, you would expect a retaining wall like this, right at the top, would simply do that, right? And it doesn't. It's still staying like that. You can see the red has centrifuge test and accompanied numerical analysis. So we're very confident. Two different methods are telling us this is what's going to happen. So you feel much more confident. And what it's telling is that as these walls want to go out, splay out, they have to create suction in between. Because I'm trying to open up and my core water pressure in here falls down. It goes into, if it goes into suction, it tries to pull the wall back. It effectively acts like a tide. Not because we designed it, not because we even knew it would have happened. As I said, the Japanese had no idea this is how these things work. But that's how they work. So the important thing was that you don't even need to have proper tiles on the top, because the and those tiles which we measured are tiny, very small. So you don't really need to worry about that. But by having the suction in the soil, probably that holds your walls together, and they perform very well. Soil is cheap, it's environmentally more green, and you use less steel. So everybody's a winner. And that's what understanding soil mechanics will do. You can deliver much better solutions with less steel, less concrete, and assured performance if you understand the mechanics properly. Okay, so let me switch back to the other set. So those are a couple of examples. Now we'll want to come and do this scaling law properly. Okay. I want to start with this particular slide. Again, as you would have noticed, my favorite test in soil mechanics is shear box test. Very easy to do, tells you a lot. I've shown you this already, but I'm going to make only 2 points with the help of this. One is that anybody, I really said any idiot, looking at that should identify 2 things. One is soil is highly nonlinear. You can't draw a little straight line anywhere in that. And it's also plastic. Maybe plastic bit you can't get from that, but you need to unload, reload to do that. But you can see it's very nonlinear. So first of all, any undergraduate soil mechanics you learned where you relied on elastic theories, you can put them in the bin now, right? So let's not worry about linear elastic behavior of soil in terms of performance of the structures. That does not make any sense. Please don't waste your time producing more and more complicated linear elastic solutions. That's not the way to go. Second point is, I also want this graph, this plot, to show something else. One, Click once. Let us imagine we picked the example of a 1 meter high dam before, yeah, and suppose in my real dam, let's say I put dense sand below it, I would be somewhere up. I'll have big stress, big strain, and maybe the stiffness I mobilize will be somewhat tangent, if I'm looking at tangent stiffness, or secant stiffness. You can choose that, but it will be relative to that point. Yeah. If I build a 1 meter high dam and worry about the stresses, I'll be somewhere here. Yeah. Low stress, I'll be in the lower part of this curve. If I worry about my stiffness, I'll have quite high stiffness because that is simply tangent to this line. If you are worrying about tangent stiffness. Now, the real dam will move. Okay, what's the consequence of that? So you build your little model with the height model, and you say, right, how much is my model going to settle? Because the stiffness is high, this model will settle less. Yeah, high stiffness, small settlement. And then if you say, oh, I'm going to predict best because I scaled it by a factor of 100, I'm going to multiply that by a factor of 100 and predict the settlement, you will get a number. Then you go and construct this 100 meter high dam, and then to your shock horror, it will settle a lot more. Why? Because once you put the higher stresses onto it, your stiffness is different. And that's the key. It's not so much we are getting the stress right in the centrifuge, we are getting the stiffness right. And that is a very subtle but important point to understand. So, with this help of this, we can say, if I make models at, okay, one more, went the wrong way. So we need to be at the right stress level and right strain level, i.e. should be there. And that's what Dan said. Same argument applies for loose sand as well. Instead of being here, you'll probably be here, and the tangent here is a lot steeper than the tangent here. It's easy to see, even easier to see for loose sand. So it's almost, well, it's a requirement, why almost? It is that you make your models work at the right stress and right strain so that you mobilize the right stiffness. Anybody not sure about that? Make sense? Yeah? This we've gone through. So all we're doing in a centrifuge is using this basic second PUC, I guess intermediate level physics to say r omega squared is my angular acceleration. You're matching that to n times g. Now, how does this look like for a typical centrifuge? I'm going to pick the Sudarshan centrifuge at IIT Bombay because I know the dimensions very well. Spent many days crawling underneath it. It's 4.25 meter radius, exactly. So if I want to simulate a 100G test, then I can work out the omega and the RPM from that omega using omega and omega, R omega squared is Ng. So it comes to about 145 RPM. So it's not, as I said, the RPM is not very big for these. The G level comes because of the radius, not so much because you're going faster. As a counterpoint, if you make a smaller centrifuge, to get to the same G level, you need to go faster. Okay, and there are some consequences for that, which you can read in the book, but I'm not going to cover here. Okay, so this is our centrifuge built in 1970s, mid-70s, and I've introduced this already to you. This is the Davis beast, the Davis centrifuge at University of California, Davis. They are American, so they need to have everything big. Their radius is our diameter. So the radius of that machine is about 10 meters, 9.1 1 or something. They cook quite close to 10. And that basket at the end is about this big. It's massive. I mean, I can stand on one corner and it won't even move. It's that big. This is the other centrifuge they have in the States. It's called the US Army centrifuge. This was done by a French company. That's why it looks beautiful. It doesn't work, but it looks beautiful. But this is the reason I put it here is it goes up to 700 G-ton machine. This, at the moment, is the largest payload capacity centrifuge in the world. And of course, US Army must have the biggest one. So they built this one. However, recently, we came to know 2 months back, the Chinese are building 1,000 1,000 G-ton centrifuge. Just, if I know when they're testing it, I'll be on the other side of the world. But most construction companies in Japan, like Takanaka, have built their own centrifuge. These things, as I said, will have the weight on the model on one side, and counterweight is just a, you don't need 2 baskets like our centrifuge. This is the new design. And this is our centrifuge in Bombay. That's quite nice. And it's actually built quite sturdily as well. So it will last, for sure. It's not easy to fail this thing. And there are many, many advantages of this machine. It's very easy to access. So we fixed a lot of problems we know exist from other centrifuge facilities. So I like this one. Also, you can buy smaller centrifuges like this mini drum centrifuge, which is built like a washing machine, and you can put soil all around it and test it. And that is another way to do this.